Welcome back, everyone, to another BGCSE Past Paper Review. Today we're reviewing a chemistry paper. It's a paper 2 from the year 2021. Please remember before you start the examination to write a school number. Very important to do so. Your candidate number is important as well. Your surname and your initials. Again, please remember to read through the entire instructions to make sure you understand each and every one before you start the examination. For the chemistry paper, they will provide you with a periodic table. You can use it as guide to answer your questions. All right, so let's dive into question number 1. And question number 1 states that a sample of muddy water was collected by students. The mud was removed from the mixture by filtration. It's a draw a fully labeled diagram to show the filtration of the muddy water. All right, and I'm gonna see how quick I could do this. So the first thing you're gonna draw, you could draw your funnel. All right, so let's draw our funnel. So that will be our part of our funnel right there. All right, so we're gonna have the next part of funnel. Mine will not be looking really nice as yours. You're gonna spend some time and ensure that your diagram is looking nice. All right, so I'm just gonna sketch something real quick. All right, so that's my funnel, and you have a flask. Normally, it's a conical flask. You could have a conical flask there. All right, so you have a conical flask is better to draw. That will be your liquid going in or your substance going in. On the filter paper, well, in the funnel, you're going to have a filter paper. I'm drawing like that to make the distinction. All right, so that will be the paper. Of course, the paper will be smooth. All right, and then you're going to have a little patch of sting right here. All right, and then you can have another smaller beaker that's going to pour the substance out into the thing. All right, so what's going to be important, I'm going to label each of these what they actually represent. All right, let me just draw a line here. Let me draw another line right here as well. Let me draw a line right here. Those three things. And yeah, I could label from there. All right, so I'm going to label all three now. Matter of fact, I'm going to label as much as possible. So this will be, here is the filter funnel. So this will be the filter funnel. All right, so that's the filter funnel. All right, and here you're going to have your what passed through the filter paper is called a filtrate. So this will be the filtrate, and in this case, it's going to be water. So water going to pass through. All right, and what is left on behind is called the residue. So that is the residue, and the residue is actually the mud. All right, make a note of that. Here is a filter paper. This will be your filter paper. So something like that will be good. And this will be a mixture in the beaker right here. So this will be a mixture of the mud and water. All right, so pretty much that will be good. And of course, if it's a conical flask, you can leave it as a conical flask, right? A conical flask is best to use. All right, because the filter funnel could sit in the mouth of the conical flask rather than a beaker. All right. Yeah, so that's answer the question. For 3 marks, yes. All right, so after the mud is removed from the water, name the physical technique that could be used to remove the dissolved salt and collect the water. And then just to make a note, because the salt can dissolve in water, so this actually, the type of water coming out here is salt water, right? So I could just make the correction there. I just add this into it. So this is salt water actually. So this is salt water. All right, just to make a note right there. All right, so if you have salt water now, what technique can you use to get rid of to collect the water? And you can use a simple distillation process. So this will be a simple distillation, not fractional, but simple distillation. All right, so this is a simple distillation. All right, so simple distillation can be used to do that. All right, here's a describe a test and the result to determine the purity of water collected in A2. So what we can do here is to describe a test and the result to determine the purity of water. So once you collect the water, what you can do is to boil the water. So you can do by boiling. So you do boiling, and what you do here is to test for the temperature. So the result here you're going to look for is the boiling point. Okay, so the result, it boils at 100 degrees Celsius. So you check if it's boiling at 100 degrees Celsius. All right, let me just put the C and then I will write T in the Take a sign. Degrees Celsius here. Yeah. So this is 100 degrees Celsius. You test if water is boiled at 100 degrees Celsius. If it is, then it is pure. If it's not, then it's impure. That means some impurities are inside of the water itself. All right, let's go to the next part of the question, part B. It says a student adds copper-2 sulfate to water in a beaker to form a saturated solution. So the solution is saturated. It says what is observed in the beaker when the copper-2 sulfate solution is saturated. So if the copper-2 sulfate is saturated, you're going to realize it's going to be dark blue, okay? Because copper-2 sulfate is a dark blue. Copper oxide is white. Remember when you had water to it becomes blue. All right, so it is going to be a dark blue color. It's a describe a test that can be used to show that the solution contains sulfate. So we'll talk about that. All right, so the test of a solution contains sulfate. The first thing I want to do is to, let me just number this. So the first thing, number 1, you're going to add few drops of HCl. And you can write out the word, please write out the word hydrochloric acid. So HCl, all right, so, and it's hydrochloric acid. So just to mention that, so hydrochloric. So do not tend to just write formula without writing the words, especially when you're explaining, all right. All right, so hydrochloric acid. So you're going to add a few drops of hydrochloric acid, and then you're going to go to another thing now. So then you go to 2, and it's a 3 marks. You're going to add a few drops of barium chloride. So you're going to add barium chloride to this. So add a few drops of barium chloride. Or you can, if you don't have drops, you can add 2 ml or 1 ml depending, right? So you can use more than just few drops. All right, but if you have a small test tube, a few drops will be sufficient. All right, so a few drops of barium chloride, add a few drops of barium chloride. And barium chloride is BaCl2. All right. All right, the third thing that you want to do here is, that you want to observe the container for precipitate. So you're going to observe the mixture. All right, so observe the mixture for a white precipitate. All right, and the white precipitate is actually going to be barium sulfate. So the white precipitate, put the in bracket, is going to be the barium sulfate that is formed. All right, so barium sulfate will be formed, and it's a white precipitate. All right, because it is insoluble in water, so it's going to be a white precipitate. All right, so good. All right, that's question 1 out of the way. All right, nice. Question 2. It said diagram shows an atom of magnesium. So there's an atom of magnesium. Here we have the electrons, the nucleus. So you can see the proton and neutrons there, and we see the electrons on the shells. All right, and so let's see what they actually asked us to do here. Here now, part A said magnesium is a metal. So magnesium is a metal. So state 2 properties of metals. And metals have a lot of properties. One is that metals, they are malleable. All right, so metals are malleable. And what it means to be malleable is that mean that they can bend easily. All right, so they are malleable. Metals tend to be dense as well. Metals tend to be good conductors, so they are good conductors. They're good conductors, and good conductors that just put heat and electricity. So they're good conductors of both heat and electricity. All right. All right. All right. So that's some of the properties of metal. All right. That's 3. A matter of fact, you can separate the good conductors into 2. Heat by itself and electricity by itself, right? Others that you need to know as well is that metals are ductile, and being ductile means it could be drawn into wires. Okay, you can draw the metals into wires. Also, they have high melting point. Okay, they're high melting point. Metals are not easy to melt at all. All right, so they're high melting point. And another one is that they have good luster, so they tend to be shiny. All right, so they tend to be shiny or good luster. All right, so that some properties there of metals. All right, this is a stated type of bonding that occurs when magnesium chloride formed. So the type of bonding that between magnesium and chlorine is ionic, is an ionic bond. So you're going to be ionic bond. And again, is between a metal and a non-metal. And ionic bond is when electrons are transferred from the metal to the non-metal. All right. All right, let's go along to the next part of question. It's a using Lewis dot diagram. Draw the bonding diagram for magnesium chloride. Use the outer electrons only. So to do this, what you need to do again is to draw the magnesium, because the magnesium will be the atom in the middle or the central atom, and it will transfer electrons over to the chlorine. So you're gonna have two chlorine. You put them side by side here. All right, so that's chlorine. All right, I'm kind of drawing kind of big, but that's fine. All right, what you need to remember now is that each chlorine has 7 electrons. Okay, so I'm gonna put like 7 electrons at 1, 2, 3, 4, 5. All right, let's call it 5, 6, and one more 7. Right, so that's the 7 electrons there. I'm gonna use a color, different color to kind of represent it differently again. Chlorine has 7, so that's 2, 3, 4, 5, 6, and 1 here 7. All right. So what I'm gonna do now is I'm gonna put a different color in. All right. So I'm gonna put for the electrons for magnesium. Magnesium has 2 valence electrons. So to give up one to this chlorine and give up another one to this chlorine. So what you realize now is that the valence shell for chlorine, they will be totally filled, right? And because magnesium transfer electrons to both the chlorine, all right, and so that will form magnesium chloride, all right, in terms of Lewis dot diagram. All right, so for part B now, it said magnesium exists as 3 isotopes in nature. You have magnesium 24, and magnesium 24, the 24 means the mass number, right? So magnesium 24 occurring at 79%, magnesium 25 occurring at 10%, and magnesium 26 occurring at 11%. So the 24, 25, and 26, those are different masses. I remember what isotopes are, right? So isotopes are the same element with different mass number due to different in neutrons. So here it asks us now to use the information given to calculate the relative atomic mass of magnesium to 4 significant figures. So what we're going to do here, we're going to do the calculation here. And so we are going to, let me go back a little bit so I could see the values there. All right, so 1 you have is 24. So first you're going to say, all right, let me type this in. I think I'll go faster with that. So you're going to have 24 for 1. So 24 going to be multiplied by 79%. All right, and 79% is the same thing as 0.79, right? So it's multiplied by 79, okay, that's 97, by 79%, which is the same thing as 0.79. That equals to 18.96. And that could be grams. You can put grams if you need. So you can put grams. All right, let's put grams. All right, let's put grams there. All right, and the other one will be 25. So it's 25 and it's 10%. So it will be 25 multiplied by 0.1 or 10%, same thing. All right, so multiply by 10%. And that will equal to 2.5. The 10% of 25 is 2.5. And that is in grams as well. All right, for the next one, which is 26, it's going to be 26 multiplied by 11% or 0.11. And when you multiply that, you're going to get 2.86. It's going to be 2.86. All right, so this is grams again. All right, so when I get the total here, so the total mass now, this is going to be the total. So the total here, you add up all 3. And so what you get here is 24.32 uh 32 grams. All right. Yeah. All right. All right. So we finished with that. All right. So let's jump into the next part of the question. Is a calculate the following. No, sorry. Complete the following table by inserting the number of subatomic particles found in magnesium 26. So this is magnesium 26 here, and we will look at the number of subatomic particles. First, we know that if the mass number is 26, that's the mass number here is 26. That's the first thing we need to know, right? So magnesium does not change. So the first thing you can actually write is the proton number. Since it's magnesium, the proton for magnesium is 12. That will never change. And the proton is equal to the number of electrons. So of course we're sure about that, right? How will we get 26 now? Is the proton minus the mass, right? So if we minus 12 from 26, what you get is 14. Okay, so you're gonna get 14 there. So 14 plus 12 is 26. All right, so that will be the number of neutrons there. All right. All right. So let's jump into the next part of the question, or this question 3 actually. So that question finished. So question number 3 is a use equation to answer the following questions. And so here we have sulfuric acid reacting with calcium hydroxide to produce calcium sulfate and water. It's a name a type of chemical reaction occurring. And if you notice, it's an acid plus a base, that is a neutralization reaction. So the acid react with base is a neutralization reaction. Neutralization, all right? The neutralization reaction. All right. Next now is a universal indicator is placed in a conical flask with the sulfuric acid before the other reactant was added. So you put universal indicator in the conical flask with the sulfuric acid before you put the other reactant. All right, it says state the color of the universal indicator at the beginning and at the end of the reaction. So at the beginning of it, since it's acidic, because sulfuric acid is acidic, so what you're going to notice here, you're going to get a red color. You're going to get it, going to be red. And you can actually say dark red. So you're going to red or dark red. And why is dark red? Simply because sulfuric acid is really a strong acid, right? So between red to dark red. It said the color at the end of the reaction, since a neutralization reaction, what you're going to form is water, which is a neutral substance. So therefore, the pH of a neutral substance, well, the color on the universal indicator is green for neutral. All right, so you're going to get a green color. It's a name of process by which sulfuric acid is produced, and sulfuric acid is produced by the contact process. All right, I think we mentioned that in the paper 1. So this is the contact process. All right. For the next part of question here, is a state 1 commercial use of sulfuric acid, and sulfuric acid has many commercial uses, and so one of them fertilizer. All right, and it is used in fertilizer a whole lot. All right, because of the great demand for agricultural products. Also in detergents. Okay, so using detergents as well, or to produce detergents. It is used in terms of making paints. And I think I've mentioned these in paper 1 when I talk about sulfuric acid and the contact process. You can use to also make plastic. Yeah, I did mention the same exact things in paper 1. All right, so for part 4, is a state why universal indicator is not used in titration experiment. And for a very basic reason, because the universal indicator displays a wide variety. So let me say it displays a wide variety, all right, a wide variety of colors, all right, for a wide range of pH, over a wide range of pH. Let's say over a wide range of pH, okay, wide range of pH, and pH is lowercase p uppercase h. All right, so that's the reason why, because sometimes it's hard for you to say, okay, this is a pH value, this is a pH value, because it does not indicate the exact pH in terms of, okay, remember, it can move from red to slight red to very dark red, and even the green for being neutral, it don't have to be exactly neutral for it to be green. It could be slightly acidic or slightly or strong base or slight base, I should say. So it could be a weak acid or a weak base, and you realize it's going to be slightly green, all right, to yellowish or to slightly brownish. So it depends on the color, right? So that it does that. It's not exact. It's not precise. It does not give a precise reading. So in titration, you want to know exactly when the reaction reach the end point. So to use the universal indicator, you will miss the end point. More likely you will miss it. All right? More often than ever, you're going to miss it, a matter of fact. So for part C, a student prepares a sample of barium sulfate, right? By reacting barium chloride with sodium sulfate. All right, so let me just quickly write this reaction here. So you use barium sulfate. So barium sulfate is what was used. Okay, so barium sulfate is formed. So barium sulfate is formed, and they use barium chloride with sodium sulfate. Okay, so barium chloride. So you're gonna have a Ba. All right, let's call it a B. All right, let me make it a little bit better. B. So it's gonna be BaCl2. That's barium chloride. Remember, barium is from group 2. Chlorine is from group 7. Let me just erase that the mistake right there. Let's see how quick I could give you this equation. So BaCl2. What is going on with this thing? All right, that's one little thing. All right, that should be okay now, I think. All right. So BaCl2 is the barium chloride that's going to react with sodium sulfate. It's going to be Na2SO4. We're going to have Na2. All right, SO4. All right. All right, I'm getting it better now. Yep. All right, soon become a pro in this. See, talk too quick. All right, right, no worries. I will get there. All right, so, yep. And so what you're going to get as an end product right here, you're going to get BaSO4. So you're going to form barium sulfate. That's how you get the barium sulfate. So BaSO4. All right, and then you're going to get as well, because this is a substitution reaction as well, plus here NaCl, but the reaction is not balanced, as you can see, based on what I have so far. It's not a balanced reaction. So that NaCl, just ignore that jumble thing. All right, so you have 2 Cl here, you have 2 Na here, so just need a 2 right here, and everything look balanced. Yep, that look good. All right, so that is definitely good enough for a balanced chemical equation. Again, you will be neater. But it said describe a method to produce a pure dry sample of barium sulfate. Okay, didn't ask us for a chemical reaction. It's not a matter of waste time though, because we're still going to use this information to kind of guide us. So barium sulfate is formed in this way, right? So I want to describe a method now to produce a pure dry sample of barium sulfate. What I need to know about barium sulfate is that barium sulfate is insoluble in water, right? So what I'm going to put here is at the first point. As the first point, the first thing you need to do is to, let me just say, since, let me give you information here, since barium sulfate is insoluble, all right, so since it's insoluble, while sodium chloride is soluble. Okay, so while sodium chloride is soluble, all right, what you're going to do is to pour some water over both of them. All right, so what you can do, you can pour the mixture. Because remember the solution or the end product. So whatever you get at the end of the reaction up there, so you're going to pour the resulting, let's say resulting mixture. So pour the resulting mixture on a filter paper. You can put it on a filter paper. Of course, it's going to be in a filter funnel and a conical flask and all that stuff. So you're going to mention all that, right? So put in a filter paper in a filter funnel in a conical flask. All right, so that's the first thing you want to do. The next thing you want to do here now is to pour water over it. So that's the second thing. You're going to pour water. So pour water over the mixture. Pour water over the mixture. And to pour water over the mixture. All right, so that's the next thing I want to make sure right there. Now, and what's going to happen here is that sodium, let's write it right here. Sodium chloride will dissolve, because remember that is soluble, so sodium chloride will dissolve. All right. All right, so sodium sulfate will dissolve and pass through the filter paper, right? And pass through the filter paper in the water, right? All right. So since sodium chloride is soluble, it will dissolve and pass through the filter paper, and let me say call this a filtrate. So this will be the filtrate right here. All right. Filtrate, leaving barium sulfate behind. So leaving barium sulfate behind. And sodium sulfate behind you, it will be what they call now the residue, right? So it is the residue. So, but what you're going to keep on adding, so what you can do again is to, let me just put another point right here. That will be very important. Here you're going to say, let me just put, because that's going to be important. So add more water, or wash with more water. Let me say wash with more water, because actually is washing the thing. So wash with more water, because once you run water over barium sulfate, actually is washing it. So run more water over the mixture, until a consistent color is obtained. Okay, and why you want that consistent color is because all the impurities now are washed off. All right, so you want to make sure the color is uniform and so on. All right, so what is left on the filter paper now? So I'm going to take that piece off now. So once you finish with that, washing the barium sulfate, wash away all the sodium chloride. What I'm going to do is to remove the remains, and remains that is there, it is the barium sulfate. Remove the remains, and the remains here is barium sulfate. All right, so remove the remains, which is barium sulfate, and dry slowly using low heat, okay? And dry slowly using low heat. Yeah, so that's how you get a dry sample of barium sulfate. All right, because remember here would be aqueous in the first place. So of course, the barium sulfate will be solid, and then the sodium chloride will be aqueous, but you want to get rid of the sodium chloride from the mixture. All right, so we're going to do one more question. We're halfway here now, or technically halfway. When we finish number 4, we actually have the halfway. All right, so for question number 4, it said chemists need to know if a reaction releases energy or absorb energy. Here it said state which of these are exothermic or endothermic. And just to point out right here that exothermic will give off heat to the surrounding or its environment. Endothermic will absorb heat from its surrounding. So condensation of gas to liquid. If you're moving from gas to liquid, the gas is releasing heat and becoming cooler. And so therefore liquid is cooler than the gas itself, so you lose heat. So therefore it's going to be an exothermic. All right, let me write out the whole thing. All right, so exothermic, right? And now burning of fuel, again, burning of fuel is giving off heat, all right? Once you burn any fuel at all, and it's a fuel for cooking, doesn't matter what type of fuel. Once you burn in fuel, you're going to give off heat. So this is going to be exothermic, okay? Give off heat to its environment. All right, this is a necessity of sunlight during photosynthesis in leaf. The leaf will absorb energy from the sun, all right? Because remember, the chlorophyll will absorb energy. So this one is going to be endothermic. All right, so it's the absorption of heat by the leaves, all right, particularly chlorophyll. All right, so part B now, we said the spacecraft fuel, dimethyl hydrogenase, has a large energy content per gram. So, nice, I said, yeah, this is shown in the table here. So the information in the table is for dimethyl hydrazine, right? So that's the information for this right here. So this is dimethyl hydrazine information. Here is an energy per mole in kilojoules per mole is negative 1694. And the negative sign means that it is an exothermic reaction, just point that out as well. And so the molar mass here is 60. The energy per gram in the fuel is kilojoules per gram is minus 1694 divided by 60. So it just divide the molar or the energy per mole by the molar mass. You should get the energy per gram of the fuel. So right here is a calculate which fuel, methanol or octane, produces the most energy per gram of fuel. All right, so what we're going to do here now, we have the same information here. We have the compounds and we have the energy per mole for each of them. So we're going to follow the same. You can follow the same example. It's the exact same thing. So what we're going to do, let me just put a line to show exactly what I'm going to do. Let me put, I could calculate here. Let me calculate methanol here. All right, so I'm going to calculate methanol on this side. All right, so I'm going to calculate methanol. For methanol, I'm going to calculate this is find the relative molecular mass first. And so carbon is there, is only one carbon, so it's going to be 12 plus. For hydrogen, you have 4 of them, so it's going to be 12 plus 4. All right, so 3 and 1 is 4 plus. The mass number for oxygen, which is 16. Okay, and so the total mass there, which is the molar mass, 12 plus 4 plus 16, that is 30 to be exact. Yeah, so the 30 grams. All right, so the molar mass of methanol is 30 grams. What we're going to do now is to divide here the joules per mole, which is a minus 276. So what we're going to do here now is to divide, let's say we're going to divide negative 726 kilojoules per mole by 30. And what we get here as a result, this will end up with a negative, let's say negative what? No, negative 24.2, negative 24.2, and this is going to be kilojoules per grams, right? So this will be kJ, kJ per grams. All right, so that's the value there for methanol. Let's do the calculation now for octane. I'm going to do it on this side here. All right, so let's, matter of fact, I'm going to do it on top right here. So I'm going to do it right here for the energy in octane. So we're going to do the same thing. The mass number here is carbon. Carbon is 8 carbons. So we're going to say 8 times 12, which is going to be 96. So 12 times 8 is 8 carbons. 12 times 8 is 96. So that's 96. Plus for hydrogen is just 18 because it's 18 times 1. So it has to be 18. The mass number here, or the molar mass, is going to be 114 grams. All right, 114 grams. All right, yeah. And now to do the calculation for octane, going to be minus 5590 divided by 114. And so the result, what we get there when we do this division, we get a negative 49.04. So this is going to be negative 49.04. All right, and it's going to be kJ per gram. All right, so yeah, so that is our answer there. So by all means, and it said calculate which fuel, methanol or octane, produces the most energy per gram. And based on our calculation here, octane is the answer. So you're going to make a note that octane will produce the most energy per gram. All right? All right. All right. The next part of the question is to draw a labeled diagram to show the electrolysis of potassium bromide solution. Now this is key because it's a potassium bromide solution, which means aqueous potassium bromide, right? So potassium, which is KBr, that's potassium bromide. And just to write the state symbol here is aqueous. So they're going to be AQ. All right, so it's aqueous form. All right. All right, so that's just to make a notation there. Now to draw the electrolysis, what we're going to do here, we're going to set up our circuit. So I'm going to just quickly draw a few things. You're going to draw a cell. So you're going to have a cell. The bigger one, those are the positive. Then we have the negative, positive. That's just a battery right there, our energy supply. This side is positive. This side is negative. And what we're going to do now, draw this, connect to our electrodes. And we're going to have 2 electrodes here. All right, so let's call this one. All right, let's do it like that. All right, let's do another one, other one like this. I usually connect in the center. Yeah, but don't worry about the drawing. It's, yeah, no, I'm not connecting in the center. All right, so get the drift. So this is going to be positive, just to make a note right there. This is going to be negative, right? All right. So what we're going to do now is to draw our container, and a container will contain our solution. All right. So what I want you to note now, since the aqueous solution KBr is an aqueous solution, which means water is a part of it. So what I want to remind you that all aqueous solution tend to produce 4 different ions, right? 2 from the compound itself and 2 from the water portion that makes up the solution. So in this we can have potassium positive because potassium comes from group 1. Br will be, I'll put all the negative on one side. Br, which is from group 7. From water, we're going to have H plus ion, okay, just to make a note right there. And we're going to have OH as well. But you need to remember the electrolysis series and which of them will be preferentially discharged over the other. And so once we know which one is preferentially discharged, then we can know exactly how to put them in terms of which one is going towards the electrode. So at the negative electrode, we're going to have our H plus ion being discharged over the potassium, okay? Just to make a note of that. All right, and over the positive electrode, you're going to have our OH being preferential will be discharged over our BR, okay? So it'll be preferred, so it'll be preferentially discharged over the BR itself, okay? So within the solution, you're gonna have K plus ion, so you're gonna have some K plus ion right there. You're gonna have also some BR floating around. And you can draw more than one of these. Again, know the electrolysis series, so you can know which of the substance or ions will be preferentially discharged over the next one. All right. And again, just to know the series as I go down the series, then they will discharge easier than the one on top. All right, so this is exactly what's going to happen here. And you can label again. So you're going to label the cell. This is the electrolyte. I'm just quickly put some labelings on as fast as I can. So we're going to have our cell or battery or energy supply. So this is our battery. So let's call it our battery. All right. We have our electrolyte. All right. We have our, all right. Now to the note is that your cation go towards the cathode, right? So the negative electrode is called the cathode. All right. While the positive ion will call your cation, right? So here we have our, I want to label it inside there. All right. So good. So the negative electrode here is called the cathode. So just to make a note of that. The positive one is called the anode. So you can also label all of those. So please label all of them, right? Anode, cathode, and so on. All right. So make sure you label that. I think this is about, how many marks is this? 3 marks. Yeah, that should be good enough. But label everything. Label cations as well. Label anions. Label all of those things. All right. Positive ions or cations, negative ions or anions. All right. So part 2 now is a state where electrolysis can occur in potassium bromide solution. I say can occur in it. So the reason why, matter of fact, electrolysis can occur in any solution is simply because it presents a ion. So it contains ions, all right? Ions that allow the flow of current. Let's say the flow of current. All right, so allow the flow of current. All right, or allow current to flow. Is a give one industrial use of electrolysis. Electrolysis is used in many different ways. It's used for one to extraction of metals, so can use it to extract metals. So extraction of metals. All right, we also have electroplating. Alright, so we have electroplating. We also have purification of metals as well. They can also help to purify metals. So purification of metals. All right. All right. So yeah, that question is over as well. So going to question number 5 now. And I have a question number 5. We only have 3 more questions to do. So it said in 1969, a Russian chemist and teacher, Dmitry Mendeleev, published a table of elements. Is how did Mendeleev organize his periodic table? And it organize it based on increase in mass or atomic weight. So let's say in increasing mass, or they call atomic weight. Okay, so that's exactly how we actually organize it. So increase in mass or increase in atomic weight. All right. So next part of question now, part B, say a section of the modern periodic table is shown. The letter that represents element in the periodic table are not symbols of element, and they're not symbols at all. They're just there to represent the element. Is I use the letters in the section of the periodic table to answer the questions. And so for part 1, it said which letter represent the most reactive metal, and the most reactive metal. And so the most reactive metal will be on the lower part of the basic group, which is group 1. So the further you go down, the more reactive the metal will become. I'm going to tell you why. Because going on the group of the metal, you have what the atomic radii increases, which simply means that the valence electrons will be further away from the nucleus, which means that the metal can lose these loosely held electrons. Because once the atomic radii is large, that means the valence electrons are further away and you can lose them quite easily. Therefore, you are more reactive. So yeah, A will be our option right here. So A is going to be the most reactive metal. It's the most reactive non-metal. Let's go to the non-metallic side right here. And the non-metallic side, we're going to include X, Y, G, E, and Z, right? All right. And so out of all of them, again, the one with the smallest atomic radius will be the most reactive one. This one here is E. All right. So it's on top this time. So notice the difference. Way down in the bottom is for metal. Way up top is for non-metal. I notice it to extreme from group 1 over to group 7. So the non-metal that has the most non-metallic property will be the one that is most reactive non-metal. The metal that has the most metallic property will be the most reactive metal as well, because it's further down the group. It loses electrons easily. In terms of electrons lost, atomic radii, yeah, those two can be explained like that. So E will have the smallest atomic radius. That means it can pull electron closer to it. All right, and therefore it will react easily. Matter of fact, the term that we use here, it is most electronegative element. And a matter of fact, this represent fluorine. We know that fluorine is the most reactive non-metal because it is most electronegative. So E will be your answer right here. All right. But if they ask you to explain, you can use that to explain it in terms of atomic radii. Small atomic radii for non-metals are more reactive because they can pull electrons closer to them. But non-metal is the opposite. The bigger the atomic radii is that they're more reactive because they tend to lose electrons easier. All right, so for part 2, now it's a letter D in the periodic table represents an element with an atomic number of 29, right? So if we represent the atomic number of 29, which is D, now we're going to ask us now, so what is the number of neutron? And if it has an atomic number of 29, we know the mass number here is going to be 64, which is copper, right? So 64 minus the 29, what you get as a result is 35. So the number of neutron there is 35. Because remember, mass plus proton, all right, the mass number is the proton plus the neutron, right? So to find the neutron, it is the mass number minus the number of protons. All right, or the atomic number. Atomic number is the same thing as number of protons, all right? All right, so let's go to part 3. It's use the letter B and Y to write a formula, right? The formula of a compound formed by the reaction. So let's go look at B and Y. First thing, I'll figure out what group they're in to actually answer it. So B and Y. So B is in group 1. All right, I'm going to do it on top right here. So B is in group 1, so we know for sure it will form a positive 1 ion. So I'll put B positive up there. And then for Y now it's in group 6. Okay, so notice Y is in group 6. Oh, that's a big Y. That's not why I was going to write the element that is in my head, is oxygen. All right, so go Y here. All right, and Y is group 6. And if it's in group 6, it means it formed a 2 negative ion because it gained 2 electrons to become 8 in terms of satisfying the octet rule, right? Or obeying the octet rule. All right, so what we're going to do to get this formula, we're going to crisscross these things. So the 1 will come down here from the B, and the 2 will come down here from the Y. So what you should get as a formula is B2Y. Okay, so our formula is going to be B2Y. So let's quickly put it on at the bottom. B2Y. All right, so yeah, B2Y. All right, let me draw it in. So we're going to be B2Y. All right, there must be 2 uppercase letters as well because a single letter in the compound, there must be uppercase. All right. All right, so next part of the question said, why would the element represented by E and Z have similar chemical properties? Let's look at what they are quickly. E and Z. All right, so E and Z, they're in the same group. Okay, so let's talk about that. So they have the same chemical properties or similar chemical properties, simple because they are from the same group, which means they have the same valence electrons. All right. So the fact that they're in the same group, they have similar valence electrons. So let's write that down quickly. All right, so they have the same number of valence electrons, right? And that is enough to make them similar. They have the same number of valence electrons. All right, and because of that, they're also in the same group. So let's put same group in the bracket. All right, I don't think I'll get the mark for same group because the chart is actually showing same group, but nothing wrong in putting it though. Because it actually explains the situation, because elements from the same group are similar, chemically similar. All right. So part 5 now is which letter represent an element that is liquid at room temperature. And so let's go back up here. All right, and just to make a note, this here will be a gas. E is a gas. As it go down, become more liquid. All right, so it become more complex going down in the group in terms of density, become more dense in other words. All right, so Z is a liquid. E will be a gas. All right, and as it go down and down and down and down in that group, it become more complex, more compressed, more dense, and the particles are closer. So yeah, so Z is our answer right here. All right, Z is our answer. All right, here now said write the electronic configuration for the ion. For the ion of the element represented by the letter G. So I want to say something, I want to be careful here. It's a write the electronic configuration for the ion, not for the element here, but for the what? For the ion of the element represented by the element G. To start this out first, let me write the electronic configuration for G first, then we write what the ion is. All right, so let's go back to the chart, looking for G. Now, a kind of easy way to do this is determine it, because here we're in group 6. So firstly, you have to know this is in group 6, right? So since it's in group 6, we know that valence electron must be 6. Group 6, the valence electrons must be what? 6. So we know the last set of electron must be 6. That's a start. Now, to determine something else now, we need to know that, hey, this is in period what? 3. Let's start here. So period 1, 2, and period 3. So if it's in period 3, it means it has 3 shells. So let's work this out now. So our first shell will maximum of 2. Second shell, maximum of 8. And our third shell, which is the last shell in this case, now it says in group 6, it must have 6. And that is for the atom. That is for the atom. They did not ask us for the atom, they asked us for the ion. So if G is in group 6, period 3, and the period is based upon number of shells, so we have 3 shells. First shell holds maximum of 2, then 8, then maximum of 8 again. So we know if 6 is on the last shell, it will gain 2 electrons to become 8. So the ion of Y will gain 2 electrons. Let me say plus 2 plus 2 electrons. Remember now, it gain 2 electrons to become 8. So therefore, it's going to be 2, 8, 8. Okay? So let's put that down at the bottom there, 2, 8, 8. And that is our electron configuration. All right, so let's quickly type that in. 288. All right, and it's for the ion, not for the atom. That's very important there. 288. The atom will be 286, but for the ion it will be 288 because it gained 2 electrons. For part C, so draw a diagram to show the bonding in an oxygen molecule using the outer electrons only. So we're going to draw that real quick. All right, so first you need to know that since oxygen with oxygen is 2 nonmetals together, so it's a covalent bond. And since you only have 2 oxygen, a matter of fact, once the same atom react with itself, you should have only 2 overlapping circles like that. So I'm going to point that out. All right, it's oxygen and oxygen, so you have 2 overlapping circles. All right, let's put our oxygen symbol in the individual circles. All right, what we know is that each oxygen requires 2, so each of them will give up 2 electrons from the other one. So I'm just put X there. So this one gave up 2 electrons. All right, so this thing want to play today. All right. Okay, cool. So here now, we give up 2 electrons here from that one. All right, and the other one must give up 2 electrons as well. All right, because that's how they actually work. Okay, 2 electrons given up from here, 2 electrons given up on another side. All right, so once we establish that, the next thing we need to establish here now is since oxygen has 6 valence electrons and each of them gave up 2, we have 4 remaining on the outside, right? So put 4 on the outside. So H gave up 2 from its 6. So we have 4 remaining on the outside like that. All right. And so this will be now our structure here showing the bonding between oxygen and oxygen. All right. So that is oxygen gas. All right. Next part of the question. No, that question is done. So question number 6 and 2 more questions to go. I said here now, it said the table contains a list of chemicals used. It said use this list to answer question A to H. All right. So we have a number of gases there. All right. So this one should be a little bit faster than before. Okay. It's identify 2 chemicals needed to make ammonia, and ammonia is NH3. So if ammonia is NH3, then we need 2 things. We need nitrogen and we need hydrogen. Okay, so nitrogen and hydrogen. All right. So those are the 2 elements needed to make ammonia, which is NH3. All right. It said which chemical is an Amphitheric oxide. And remember what amphitheric oxides are. We talk about it in paper 1. And to be amphitheric, it simply means that you can react with both acid and base to form salt. But again, the oxide that will form either acidic, form basic, or amphitheric will have to be the metallic oxides, right? And so the metallic oxide, we have 2 of them, matter of fact. We have sodium and we have aluminum. But sodium will only react with the base, of course, but aluminum will be a little more complex metal, so therefore it's going to form both. It can be between both. So aluminum oxide will be the winner in this case. All right, so aluminum oxide is the winner. Aluminum oxide. All right, so that's the winner right there. All right, so aluminum oxide is the amphitheric oxide. All right, and say part C now is a name 2 chemicals used to make chloromethane. And chloromethane actually have 3 different elements there. So that was going to show you something if all of them up there. We have carbon in there, yes. We have chlorine and we have hydrogen. So yes, so we can enter any of 2 of the 3. Okay, so there are 3, but we can enter 2. So let me just give you all of them. So we have carbon. We can also could have hydrogen, or you can also list chlorine as well. So depends on how you feel. And again, they may not ask the same exact question, right? But at least you know what are made up. You have carbon, hydrogen, and chlorine. All right, so it's a name the lightest gas. The lightest gas, let's go back in chat and see. Lightest gas is hydrogen. As we know that hydrogen is very light. It's the simplest gas, mass number of 1. The lightest gas here is hydrogen, okay? Hydrogen. It's a named solid that reacts with water to form an alkali. So the name of a solid that will react with water to form an alkali right here is actually going to be sodium oxide, right? All right, so sodium oxide, and I'm going to show you the reason why. So the sodium oxide, all right, so it's in the chart, sodium oxide. I actually saw it there. So sodium oxide, yeah. So sodium oxide it reacts with water to form an alkali. I'm gonna tell you the alkali it's gonna form right here. So if you think about it, right, it's just reason through it you're gonna see. If sodium oxide, so NaOH, right, reacts with water, gonna form sodium hydroxide, and hydroxide is an alkali, all right. So hydroxides are alkaline. The only other metal there, let me see if there's another metal there. If you think about aluminum oxide, it doesn't react with water so easily. All right, yeah. So yeah, sodium oxide, yeah, that's okay. All right, it said name the alkaline gas. Name the alkaline gas, and the alkaline gas based on the chart right here. The alkaline gas and the gas, it has ammonia actually. All right, ammonia is the alkaline gas. Ammonia. Yeah. All right. So let's say ammonia is the alkaline gas. It's a name the catalyst used in the Haber process, and the Haber process uses iron. I really don't need to go back up here for that, but it's iron is the catalyst in the Haber process, and it's actually in the chart. All right. It's a name the substance that make up 20% of atmosphere, and this is oxygen. Actually, it's run off to be 21. Now, if you're in bio class, you'll know that is oxygen is this gas that make up 25% of atmosphere. Okay, it's 21% average. Yeah, so it can be 20 as well. All right. All right, next question, which is question number 7. We have one more question to go and we finish. Is that organic chemistry is an important branch of chemistry. Is that which element is primarily a part of organic chemistry, and this is carbon, because organic compounds are actually carbon compounds. So carbon is the major element. It's the alkanes and alkenes are two homologous series. Explain what is meant by the term homologous. And there are many ways you can actually define this, or there are certain things you need to mention when you're defining this. Is that one is a group of organic compounds. So it's very important that they are organic, okay? So a group of organic compounds. All right, so a group of organic compounds with similar properties, all right, with similar properties due to the same functional group. Okay, so they have the same functional group due to the same functional group. All right, what is also important too, they have the same general formula. They have the same general formula. All right, and the next thing I want to mention here is that and each member, let's say, and each member differ from the other by a set number. All right. It's a draw the structure of an alkane with 3 carbons. That's the next part of the question here. So draw an alkane with 3 carbons. So alkane, they are single bonds. They are saturated hydrocarbons. And so if you say 3 carbons, the first thing to draw is the 3 carbons, and then make sure that they are single bond between each other. That's alkane, ANE. And then remember that each carbon can have a maximum of 4 bonds. So you're going to make sure that you have 4 lines around each carbon like that. Each carbon has 4 lines because they have formed maximum 4 single bonds. And each of these lines, you could put the H's on them. all right, to make it complete. And that's a simple draw organic compounds. Each carbon can only have 4 lines, right? No matter what you do, 4 lines around each carbon. And once you establish that, you just put in your H's at the appropriate places. All right, and so this, you know that this is called propane, right? All right, so this is propane. Okay, so we're good at that. One more and we finish. All right, so let's jump to the next part here now. The next part is draw the structure of an alkene. An alkene is a double bond, right? With 3 carbons. You're going to draw your 3 carbons. All right, it doesn't matter if we put the double bond, it could be any of the ends, it really don't matter. So the fact now you just have 3 carbons, that's the most important thing. Again, each carbon must have 4 bonds or 4 lines around them. So I'll put this as a single bond right there. So since you have 2 lines right here, you're going to have only 2 more in this one. Okay. This one has 1, 2, 3. So this one only need 1 more. Doesn't matter if you put top or bottom. This one has 1, so you need 3 more lines there. And the lines are just single bonds, right? I'm saying lines just make it easier. But the lines actually means single bonds. You have 4 maximum single bonds. All right. So the lines, no matter the combination, could be triple and single. 2 double, doesn't matter, but you must have 4 lines when you're drawing any organic compound around the carbon atom. All right, so we get this line out. All right, let's go back to putting our H's on. All right, so that is propene. Okay. All right, let's look at part C now. For part C, is to name the type of reaction that occurs when an alkane reacts with brine. And there are actually 2 with bromine. I said brine, with bromine. So when alkanes, when an alkane react with bromine is from group 7, they're called halogens. So this reaction is called halogenation. So this is called halogenation. All right, and halogenation is also what you can call is a substitution reaction as well. So halogenation is a substitution reaction. All right, just to make a note of that. All right. And how we know it's a substitution reaction, because remember it is all single bonds, so you'd have to replace some of the hydrogen for it to actually happen. Okay. All right. So halogenation is the reaction, or as we stated, it is a substitution reaction or a substitution reaction. All right. So yep, there we have it. And for part 2 of C, now we said many alkene molecules join together to form a polymer. State the name of the smaller unit that forms a polymer. The smaller unit that forms a polymer is actually called a monomer. Okay, so a monomer is a smaller unit that forms polymer. All right. So next part of this question, right? This question not finished yet. It said homemade wine can be made by putting yeast in grape juice. It's a name this process. And this is actually called filtration. Fermentation. I'll say filtration. All right, so it's called fermentation. All right, so fermentation. All right, and it said, explain the job of the yeast in this process. So the job of the yeast is actually to respire. So you're going to use the sugar, to use the sugar. All right, so use the sugar for respiration. All right, for respiration, and in turn, convert the sugar into alcohol or ethanol. Okay. All right. So while the yeast is using the sugar for energy for respiration to produce energy, in turn, what it does is to convert the sugar into alcohol. All right, so alcohol is formed as the byproduct of the fermentation of yeast, or the respiration process in yeast. All right. Last question and we finish. Now it said the catalytic converter was invented for the use in cars in 1970s, right? Here now it said gasoline in the 1970s contained a chemical which damaged the catalytic converter and also poisoned human. This chemical has been banned from the use in gasoline, and they said name this chemical, and this chemical is lead, because you used to add lead to gasoline to make it leaded, and make it heavier and take a longer time to burn out. But of course, it causes some other problems. Again, as I mentioned, one area is to damage a catalytic converter, and lead could also poison us as well. All right, so we can have lead poisoning. However, part B is a sulfur is a byproduct of petroleum and natural gas processing. It's a name a gas formed when sulfur comes in contact with gases in the atmosphere. And this gas going to form is actually called sulfur dioxide. Okay, this is going to be sulfur dioxide. All right. And sulfur dioxide. And sulfur dioxide is SO2, just to make a note of that. All right. It's when this gas reacts with water, it causes a phenomenon in nature. It's a name this phenomenon. And this phenomenon is called acid rain, because it make the water acidic, so they call acid rain. All right, acid rain. All right, so part 3 now. It said state the effect of this phenomenon on stonework and also metals. So the effect on stonework, because of the chemical nature or the acidic nature of the water, what it'll do is it cause the rocks to weather. So you're going to cause weathering. So weathering of the rocks, okay? So weathering of the rocks, which means over a period of time, it decays the rock, or to break down the rock slowly. All right, let's use the word breakdown rather than decay. All right, you can use degrade as well. So degrade the rock or break down the rock over a period of time. Effect on metals is that it causes corrosion. So you're going to corrode the metals. So you're going to say corrode. So you're going to corrode the metals. All right, so corrode metals, or corrosion of the metals. All right. Yeah, because the acid is corrosive to the metal. All right, so let's say corrosion. All right, corrosion of the metals. All right. Here now, it said petroleum is a finite energy source. Define the term finite. So it's a finite energy source. What it means to be finite in terms of energy, it means that a state of using, so it means that using the resource, faster than it can be replaced, all right? Faster than how it can be replaced, okay? So, yeah, so that's what it means. All right. So finite means that you have a limited amount, you're using faster than you can replace. It takes a really long time to make. All right, and we also call this our non-renewable resources, right? It's a given example of an alternative energy source, and there are so many we can talk about. We have wind, all right, we have solar, we have water, and water is what they call hydro energy. Let's say hydro energy. All right, so we have hydro energy. We also have geothermal energy as well. Geothermal. All right, so we have that as well. Let's see the next part of the question, what the question is saying here. It says sulfur dioxide is used as a preservative in foods today. It says explain briefly why food are preserved. And food are preserved typically is just to increase shelf life. So I'm going to give you 2 reasons right here. To increase shelf life, okay? To increase shelf life is 1. And also to maintain freshness, and appearance as well. To maintain freshness in foods. Yeah, to make the food remain fresh for a longer period of time as well, which is similar to increasing shelf life as well. All right, so it is prevent spoilage. So you can also have that as, again, to prevent spoilage, to make sure food is available, and things like that. Is identify another food preservative. And another food preservative, a very basic and common one is salt. All right, that's very basic. Salt can be used to preserve food. But on a commercial level though, well, even though salt is used commercially to preserve certain food, also we have here sodium benzoate, and you may see that in some beverages sometimes, right? So we have sodium benzoate. All right, so we have that. Also, what we have again is also potassium sorbate. That's a common one. Potassium Sorbate. Okay, so yes, that's another one there. All right, so we're at the end of it. And again, thank you for being here. And I hope you do well on your examination. Talk to you soon. And you'll see me again for another review. Keep safe and keep blessed.